So welcome to today's Developing Secure Systems Summit talk. I'm very pleased to introduce Greg Kroah-Hartman. Greg is a fellow of the Linux Foundation. He maintains the Linux kernel stable versions, the staging drivers, the sort of incubator for new device drivers, and a really large number of other subsystems. Indeed, a quick check through the history of the Linux kernel shows that he's authored commits in over the support for over 40 hardware architectures, USB, file systems, networking, and so on. At the same time, he's been very proactive in attracting new Linux kernel developers through a variety of talks and through formal and informal mentoring activities. Today, he will tell us about non-technical security best practices for open source projects. So if you have any questions, please feel free to, if you're in Teams, in the Teams chat, or if you're looking in YouTube, in the YouTube chat. So please feel free to ask questions at any time. So, Greg?
Okay, thank you, Julia, for introducing me. We had some technical difficulties connecting another Linux box to Teams, so I'm gonna have to say next for each slide. So if you can go to the next slide. This talk is actually based on a talk I gave at an application developer summit, and it turns out that a lot of the issues involved with security best practices are just good best practices for any type of project, no matter what it is. So be it closed source, open source, application, library, kernel. So I'll talk about some specific things as we go on there. So the slides are all online. I think they're going to be linked somewhere on the website later, and they're downloadable for free there. So if you go next slide. Like Julia said, I've been a kernel developer for a long time. I maintain the stable kernel releases. Linux does the development releases once a week. I do stable releases a couple times a week for different trees. I've been a member of the Linux security team since the beginning. It started in 2005. I'll talk a little bit more about that. And I maintain a few user space programs that you rely on in various bits and pieces. I started UDEV, which now everybody uses to boot, and some other bits and things. And I've also worked on at least 6 different Linux distros. So I know how this stuff works. I've been around for a long time. I've worked for Linux distros, volunteer and professionally, and now work for Linux Foundation. So I've been involved for a very long period of time with this stuff. So next slide. So let's go. What this talk is not going to be about anything about security theater, nothing physical. My son first thing said, oh, make sure people guard your servers with big baseball bats. We're not going to talk about that. Or I'm going to talk about language choices, nothing technical about that. We're just going to talk about things that apply to everybody and to all projects, no matter what they are. So next slide. There's a bunch of documented things. This has been written down. I'm not the first to talk about this. Many people have done lots and lots of really good research, and I'll point you to this, and I'll highlight one little thing that the Linux kernel does, because people like hearing about what the Linux kernel does. And then I'll also talk about some undocumented things that it turns out matter even more than the documented things. All right, let's go on. Next slide. So here are the documented things. The Core Infrastructure Initiative was started by the Linux Foundation a number of years ago. It's kind of merged into OpenSSLF, I think it is now. But they've documented all this stuff. David Wheeler's done a wonderful job. And if you have an open source project, go to bestpractices.coreinfrastructure.org and you can get a badge. You can quantify your project versus all these lists of things. You can see what you need to work on, what you don't need to work on. There's links to the research. There's documentation about what to do. There's all these really, really good, wonderful things. Next slide. And here's a lot of the different things they do. They talk about version numbering, reporting, release notes, build systems, all the technical things involved in this type of stuff. Really, really good stuff. I highly recommend it. It's not rocket science. You can play it like just Pokemon, go down the list, catch them all, change your project, add a README here, add this documentation there, and you can get the badge. And that shows to others that you are an active project, you're doing the best practices as far as research goes, and that's a really good thing to do. So please do that. There's no reason project should do this. It's all free, it's all released out there. It's been there for a long time. So let's talk about one thing that the kernel does, one thing that I've actually run into with other projects when I've tried to report problems. So next slide. Here's the technical thing. And the big thing you need to do is you need to have a way to report problems. a lot of projects don't have this. Make it obvious that here's how, if somebody comes along and they find that what they think is a security issue, they can report it to you. This will cause some churn. This will cause some extra work on developers, but they need to have a way to do this. So this is one thing on the technical list, and this is one thing that the kernel has done for a very long time. Next slide. We have a very simple thing. We have one email alias, send anything to that, and it goes to about 10 to 15 of us that are on the security team. We read it, we're all around the world, so pretty much it's less than 24 hours response time. We'll get back to you. We'll tell you if it's real, if it isn't real, or what it is. So next slide. So we created this back in 2005 because we kind of had an unofficial way of talking. You could email a few random people and they'd let you know what's going on. We created it in 2005. There's a link there to how we created it. 2005 was a really big year for Linux kernel development. We had just stabilized. We just agreed that we were never going to break anything anymore. We're not going to do it. We changed our development model. We created a security at kernel.org, created the stable release processes, and oh yeah, Linus wrote Git. 2005, a lot of stuff happened. So this is a security, one alias goes to the right people. These people on the group change over time. The main goal of this group is not to necessarily fix the problem, but our job is to grab, read it, triage it, and then go grab the right developer who is having this problem or who knows this problem better. They know it, we'll grab them in and we'll have them fix it. So that's our job. Get it, fix it as soon as possible, push the fix out. In the kernel, we treat a bug as a bug as a bug. We don't treat anything necessarily special than other things. We just fix it and we move on. Our rules are, we have a 7-day embargo limit. We will only sit on a fix for 7 days after we have a fix. We have sat on things for over 6 months because we haven't been able to fix it. Or we just haven't had the right person to fix it, or just other things happen. Things fall through the cracks sometimes. But once we have a fix, we only want to be able to hold on to it for 7 days. And that's really the best thing to do. We don't like long embargoes. They don't really work. We push it out. We can't sign NDAs. We're all there under individuals. We're not there under auspicious of any employer we are. We're a bunch of volunteer people, so we can't sign NDAs. We don't assign CVEs. I've given a whole talk at the Kernel Recipes conference about why CVEs don't work for the kernel. If you want a CVE, there's actually a link. You can go grab your own CVE and submit it. Fun fact is, in that link now we are asking for CVEs for every single stable kernel release. So we're giving about 20 to 30 CVEs a day for the Linux kernel, which is kind of fun to abuse the system a little bit. But so like I said, our job is to drag the people that are responsible for this in and get it to fix fast. The way you get on the security alias is if you're drugged in too many times. So we just don't want to do the extra hop. So so-and-so works in the core VFS stuff. We're tired of grabbing them in every single time and have to rebounce the message to them. Just add them to the alias and away they go. That's the way the group has grown over time. People dropped off over time as well. We have a whole document of how this works, what is involved, right there, security bugs, HTML. You Google it, it comes up really easy. Again, very, very simple and very well, good point of contact. So next slide. Let's talk about what we do. We get a lot of really interesting things. A lot of people, of course, don't really understand security, or they think they have found something, or they don't, and that's good. We will want you to defer to the fact that, oh, maybe we found something, and then we say, no, it really isn't. So a lot of the work we get is saying, no, this really isn't a problem, go report it over there. One big example is there's lots and lots of fuzzers being run on the kernel. Sysbot from Google, Dimitri's done amazing, wonderful work, but the majority of those things are all public. And if anything's found by Sysbot right now, we just say, go talk about it in public. Don't worry about it. And in fact, a lot of bugs that people are finding, I'll point to Bluetooth recently, they're finding by code inspection and whatnot. It turns out Sysbot found them 6 months ago and posted them publicly. So go talk to them in public, go work on them in public. We don't care about something. Once something's been mentioned in public, we'd much rather have it done over there in public on the mailing list with all the developers involved, because that's the best way to do it. We make sure things work better that way and it works out a better way. So that being said, I think we average, I haven't really done the numbers in a while, but we're averaging about one real security issue a week. And real meaning something can crash somehow. These are user ways that they can crash the kernel, or user ways you can read data, or user ways you can do other different ways. Things. We have a lot of mitigations in the kernel these days. We have hardening and lots of other good stuff. So a lot of things like dereferencing a null pointer nowadays don't really cause a security problem. They cause a crash. Still good to get those fixed, but they're not necessarily security issues. But hey, if you can report it to us, we'll fix it and get it done fast. So that's what we're averaging about a week. So next slide. So one thing that we love telling us how to reproduce problems. We don't like vague things. We like reports with the fixes. The first thing that we will ask you to do is if you report a problem, we'll say, hey, do you have a fix for this? You can test this best, and we'd like to give you full credit for it. And we want reports from people who want to make Linux better. That's what we want. We get a lot of reports from people who just want a CVE to add to their resume. They don't want to do anything help with it. They don't want to actually fix the problem. We want people who are actually going to fix the problem. Now, if you don't know how to fix a problem or need help with that, great. That's what we're here for. But just don't throw things over the wall. We have a lot of third-party code bug companies that get a report from somebody else and try and filter it through to us. And then there's a middleman in the way, and that's just horrible, and that never works. So if you go to the next slide, it kind of segues into the things that we hate. Maybe next slide. There we go. Again, public bugs. So a lot of these reports we get sent in Word files. And don't send Linux kernel developers on the security team a Word file. We're just going to delete it. PDF files, even that we delete. Just give us text. Plain text works great. We can all read it. Again, third-party organizations, we don't want to be the middleman. We don't want to have you talk to somebody else and have to get back to us. And it just doesn't work. Just have the developer, have the person who found it, talk to us. Again, we don't like CVE assignments, and then we don't like companies that ignore us. So sometimes companies will report a problem and then they'll just ignore it, or they'll just disappear, or that they have developers that work for them in areas that we care about, and then they don't let those developers work on the problems. That happens too. That is annoying, and that forces us to work on security fixes in areas that maybe I don't know the best, or other people don't know the best. We'd much rather have the maintainers and owners of the code work on the fixes themselves. We have a few companies that kind of ignore this. They're hopefully getting better. It's a pain, but we don't like that kind of stuff. So along that line of thinking, next slide, we have had some companies that just route around us. Some companies, and I will call out Intel, with the big giant Spectre meltdown nonsense. They did not want to do it, and they insisted that this was different. And that was a quote from one Intel executive who then retired after the whole brouhaha. If you go to the next slide, Intel decided to want to work with companies. Companies like working with companies, and they don't realize how to work with the community. And that's, to be fair, that's what they're used to. They're used to having meetings with, Intel's used to having meetings with this hardware vendor or this operating system vendor, and they're used to having weekly meetings, actually, and all this type of stuff. Weekly meetings do not scale for a security team, because I don't want to have a weekly meeting with every single hardware company. That's just not going to work. We do not do that. So Intel wanted to work with companies, and then Intel wouldn't tell what the other companies were that they were actually talking to. So for example, they talked to Red Hat, they talked to SUSE, they talked to Canonical, and they siloed these people. They wouldn't let the Red Hat people talk to the SUSE people. They wouldn't let the SUSE people talk to the Canonical people. And so in the end, they all had to create fixes individually. And then there was the open source community people, which they notified finally really late, and they created another implementation. So when Spectre Meltdown was released or made public, we had like 4 or 5 different implementations. We had to reconcile, we had to figure out which one was the best one and merge it properly. It turned out the end result was even something different than all the original ones. And also the hugest and the biggest thing that Intel forgot is that the majority of all Linux users do not actually use a corporate distro. I have some unofficial numbers for some big cloud companies, just big cloud companies or big serving companies, that they say over 75% of their users use a community-based distro, meaning Debian, meaning Fedora, meaning OpenSUSE, Arch, or roll their own. Akamai rolls their own kernel. I mean, they're known for that. They do a great job. Cloudflare does their own kernel, and that's great. That's wonderful. They forget that the majority of the world out there actually relies on the community stuff. Debian runs the world, and Debian's not a corporation, doesn't sign NDAs. Debian was not involved in Spectre Meltdown. And the things that came afterwards, the other Spectre variants, Debian was forgotten again. And even though we insisted that they'd be drawn in, they were forgot, and Intel had to learn from that. This was a total and complete mess. Now, to be fair, our normal idea of having embargoes of only 7 days doesn't really work with something huge like this, where you have to change hardware, you have to get updates out there, you have to push out microcode, you have to test this stuff. 7 days does not really work for when you're dealing with hardware situations. So kernelsecurity.org is really good when the bug is us. The bug is us with Linux. We needed to come up with something when the bug wasn't necessarily with us, the bug was in the hardware, or the bug was something that shared across operating systems. Because again, the Spectre meltdown was shared across operating systems. In the end, we ended up talking and working with the Microsoft kernel developers, talked to Zen developers, Solaris, Open Solaris developers. We had all these different people working together because BSDs, of course, because we all needed to solve the same problem to solve hardware bugs. So if you go to the next slide, because of all this, we had to create something new. Working with Intel, we created something new we call hardware security at kernel.org. And our job is a different group, 3 of us on this alias. And what we will do is we will spin up a custom team for any issue reported to us. So as an example, maybe a year ago, we were told about the issues with Thunderbolt, low-level issues that was in the hardware, needed to be fixed. Turns out it was actually at the BIOS level. It wasn't at the operating system level. We couldn't do much, but we spun it up. We got a group of people, tried to drag in some other hardware people, and tried to fix it that way. And we can do this. And we do it as an encrypted email. You send out the mailing list as an encryption key, all that code to do an encrypted mail. Mailing list is all public now, thanks to Thomas Gleixner. He did a really good job. And it works really, really well if your email systems can handle GPG or SMIME. Turns out Intel's email systems can't handle GPG, yet they required us to use GPG. Go figure. And we don't sign an NDA. We have a memo of understanding of what we do and what we cannot do. We're not going to blab this stuff to the world. And we negotiate the embargo based on when the hardware is going to be fixed. Some of these things are like 6 months out. Depends on the hardware. We've had some being reported to us. It's like, hey, this might be fixed in a year. We're like, great, we can't do anything until then. Talk to us later because I don't want to set anything. This is there. It's documented really well. We have buy-ins from all the hardware vendors. We've had to use it a few times. Funnily enough, Intel does not use this. We have not had this for any Intel issue. Intel still enjoys routing around us. We're slowly working on that. That's a community versus Intel issue. So those are the documented ways that we handle, hey, I got an issue. It might be security related. We need to get this fixed. So all software projects should have a really, really easy way to do this. This is the way we do it. 2 different email aliases handle the 2 different types of situations where the bug is with us or the bug is with the hardware. Because the whole job of a kernel is to paper over the bugs in the hardware. That's just our job. So go to the next slide. Oh, first, Julia, is there any questions on this? Is a good breaking point. I can't see.
No questions so far.
Okay. All right, so let's talk about, those are the easy ones. That's the documented stuff. Let's talk about a few undocumented things. And these are things that are good for projects to do, and they turn out to be very, very security related. Go next slide. The most important thing is you have to make your project easy to upgrade. You have to take away any barrier to upgrade, because if you have a security fix, you want them to take it. So if you go next slide. Along those lines, you can't make your users mad. You can't do things in upgrading or updating and make a user mad to prevent them from upgrading. It's that simple. You have to take away all the barriers. So depending on your project, you need to have different types of ways to work with this. So go to the next slide. So let's talk about 3 different things. There's 3 different types of developers I'm going to focus on. I'm not going to talk about embedded, but really you're kind of one of these 3 things: kernel, library, or application developer. So next slide. So kernel developers, next slide. We have one rule in the kernel. We cannot break user space. We made this rule in 2003. We can't break user space that you notice on purpose. So we do not break, if we accidentally break something, we will fix it. That's the highest priority. That's when people, only reason kernel developers get mad at each other is when somebody breaks user space on purpose. So do not do that. And we have one big rule of this. Microsoft actually did this years and years before we did. If you go to the next slide, we want never to have stop somebody from upgrading. We want you always to be able to upgrade. And we made this guarantee back in 2003 to user space, to all users of Linux. You can always take a new version of the kernel, and we will not break your user model. We will not break your user space code. We will not break what you do. We will not break what you do. And then that's way if we can get people to upgrade. It's that simple, because if they feel like they can't upgrade, they won't, because they're worried about something's going to break, they won't do it. So if you go to the next slide. This is a big quote. I think it's been said a while ago. If you are going to break your system, they get afraid and they will not upgrade. How many times have people said, we're not going to upgrade this stuff because we're worried it might break? We want to take that worry away. It has to not be there. And by doing that, like the Linux kernel developers, we test a lot. The normal development tree is tested every day. All the different trees are merged together. We test them on all sorts of different systems. The stable kernels are tested and by actually probably more different systems than the development kernel. And when the testing passes, then I'll do a release. And we have proof of who tested what. We test 10,000 different user space tests by one vendor on different architectures. We got a lot of other stuff going. We want things to not break, and we want to make sure that they never break. So if you go to the next slide, it's the same idea. They will not take your security fix because they're worried it's going to break. So if people are ever hesitant, they will just not upgrade. So you have to take away that worry. So as a kernel developer, that was our goal. We had to make sure it would never break it. So if you go to the next slide. So the way we do that is you have to keep supporting things until there's nobody. We famously kept a whole sub-architecture of a CPU type just because there was 2 machines in the world. One of them died, and then we finally got together and begged and pleaded and got the other machine to shut down too, because we're tired of supporting that stuff. It was 2 people's hobbyist stuff. But we will keep things running if there are real users. A famous 68K processor type, active developers, active users, we will keep supporting that thing until there is nobody using that anymore. And that's what you have to do. If you're throwing code over the wall for other people to use, you have to support them. Otherwise, they will go somewhere else. So if you go to the next slide. So the way you do this and get people off is you can evolve things over time so that nobody notices. You can watch when user space finally upgrades and stops using certain things. You can figure out how things work. You can provide workarounds. You can find new system calls. You can extend things. If you go to the next slide, you just evolve. I mean, the way you do software development over time, which is a whole different engineering process than it is to do a brand new release, is you have to provide new ways of doing things and support the old ones at the same exact time. That's what you have to do. And if you go to the next slide, we have done that with Linux. I have heard many times by people saying Linux is a stodgy old operating system, old user group system model with POSIX APIs and whatnot. And they're like, yes, that does work because we can run your old applications from 30 years ago just fine. But also we do a lot of brand new things. We do stuff like eBPF. We are a microkernel now. We have IOU ring, which is high speed, very, very high speed, asynchronous IO that's done without syscalls. We have a real-time. Linux kernel is a real-time operating system. I can plug in my son's guitar, to a Raspberry Pi and have it do DSP thing on real-time. Works just great. Infamously, Linux is running in many, many real-time systems, in guitars, on on stages, lots of other different places. These we do on top of the POSIX system. We have new APIs, we have new ways of thinking. So if you're just used to seeing the old model, yes, that's still there. And that's a valid model because we want those users, but we also do new things and you can grow and do that. And that's what you have to do. Maybe someday we'll be able to get rid of some old things. Slowly we do drop some old hardware support where we figure out that nobody's really using Token Ring anymore. We drop some Wi-Fi, extended Wi-Fi stuff that there was no hardware around anymore. ISDN actually part of ISDN still running because we're still using some ISDN. But other parts of it we have to rip out. That's what you have to do. You have to evolve over time. And you can do that. So next slide. By doing this over time, you have to create that trust. You never want to break a user's workload. You don't know what it is. They're using you for a reason. The only reason, nobody's forcing you to use Linux, but if they're using it because they want to do something. Let's not break what they want to do. So if you go to the next slide, we really learned this the hard way. When we went through the 2.4 to 2.5 to 2.6, we used to have odd and even release cycles with development and non-development, and we broke lots of things in 2.5. We backported things to 2.4. It was a total nightmare. That was a 2-year span of time. After 2.6 came out, go next slide, in 2003, we said all releases are stable. So every 2.5 to 3 months, we do a new kernel release, it's stable. We guarantee it. Nothing's going to break from the last release you just did 3 months ago. Upgrade. There's no reason you shouldn't upgrade. In fact, we do things to new kernel releases to make them go faster. Infamously, we've done things that no other operating system would ever do. We rewrote basic locks. Linus got bored and fixed up some new things. We take advantage of new hardware, and we can make things go faster than it didn't on older workloads. We want you to upgrade, and we want you to upgrade just for new features as well as all the security issues. So when we do a security fix, a lot of the times we don't know we're fixing security issues. We just push out fixes because we know they're bug fixes. Infamously, some security fixes are not, or some bug fixes turn out to be security fixes years later when someone analyzes them. When we're fixing 20 to 30 fixes a day, it's kind of hard to audit them all. We just say take them all because we test them all together, take them all, and we keep on going. All releases are stable. Always take them. No failure to upgrade. So, next slide. That's for kernel. So let's talk about library developers. Library developers are.
So could I ask you a question, actually?
Yes, please.
Okay. So when you say we never break things, and so you should be happy to upgrade, you really focused on sort of the functionality of things. But what about other things like the performance or energy usage or something else that people might tune a lot for?
Yes, so those are actually good things. And if they regress, we fix them if we can. We have infamously newer kernels run faster and better, less power than older kernels. If we regress in this area, let us know. We will grow in size because we add new features, but hopefully we should never slow things down. There are some documented cases where we have had to regress in certain areas. We do talk to the people, we see if we get their buy-in, et cetera, et cetera. But you should never have to stay in an older kernel just because it's slower or just because it uses less power. Then we messed up. Let us know.
Okay, thank you.
Anything else? Okay, let's talk about library developers. Next slide. Your worst, it's the worst job. I really pity you. If you go to the next slide, it is really the hardest job of any type of developer. And the main reason about this is, if you look at the next slide, when you're creating a library, you're creating an API, you never know if it really works or if it's really useful until you get people using it. And once you get people using it, you can't change it because they're using it. So you learn about how things work best after they're actually being used. Evolving a library over time is really hard. Changing APIs over time is really hard. You can't break things. It's a very difficult thing. This is a very difficult task. Library authors are the unrequited developers of the world. They have a very difficult task. Feel very sorry for them. It's rough because you go to the next slide, they can never break anything. If they break something, they hear about it and a developer will just stop using it, or they'll pin the library to an older version and never get any security updates. It will not do that. They never want to have that happen. You always want to be able to go to the newest version. You want, again, never to take any fear away of being able to update. So if you go to the next slide, the only way you can fix a broken API is if you create a new one. When you do that, if you go, then you have to do APIs you have to support. There's ways of doing this where you can have your old API, new API or new API or old API and do that. We've done that with some low-level libraries that I've worked on. It's still difficult. It's a lot of work. You can evolve things over time, but it's really tough to do. I feel sorry, but that's the only, if you want to write a library, this is what you have to do in order to get people to use it. If you go to the next slide, a really good way to start out with is be really strict in what you accept. We've had to do this for the kernel, for system calls and other interfaces. We don't let you send I would say undocumented or uninitialized fields. We make sure that they're set to specific values to start with. We want to be very strict in what you accept. Postal's law is not there for APIs. You do not want to be gratuitous in what you accept. You want to be very strict because you need to bound your rules somehow, or bound your API and bound what your usage is going to be. Otherwise, you will have big problems. We've seen this happen with APIs and libraries that try and accept everything. It just doesn't work. If you go to the next slide, Rusty Russell, many years ago, was a kernel developer. Now I think he works on Bitcoin, funnily enough. Wrote a really good blog post and had a good talk about how to write an API. There's a whole different scale from -10 to 10 about your API. -10 being it is impossible to get it right to use it, to +10 being it is impossible to get it wrong, and it pretty much writes it for itself. It's really good. If you have to write APIs, go read this stuff. He laid it out many years ago. I think it's almost 20 years now, and it still holds up today. It's really good. So we go to the next slide. For security stuff, you have to support old APIs. Otherwise, again, people won't update. You have to support the old stuff. And you want to provide guides on how to move to the new APIs. You want to provide hints. You want to say, hey, it'd be great if you could move to this old one. You don't just drop stuff. I have a program that upgraded on my distro today that a library was using it and it broke because the old API is no longer there. That program just doesn't care about other users of it. To be fair, that's what they document, but that's not a really good way to do this. If you go next to the slide, documentation really, really matters. How many times have we seen Stack Overflow examples to just try and get this stuff right? Do not do this. Good APIs need good documentation. Good projects, if you want to have a library, depend on you. You have to do this right. Next slide, I will say, you only evolve by addition, you never remove. So how many libraries have we seen where they have attribute deprecated, so you build and all of a sudden you see all these warnings start apply? That is not okay. If you, as a library developer, do this, you're saying, I'm giving up, I'm not even going to try and handle this type of stuff, you're on your own. And if I see that, I'm just not going to use that library anymore. You're just going to write it yourself, or you're going to do something else, or you're going to fork it and pin it to an older version, and then it'll never get updated. You don't want to do depreciated. You can wrap that stuff yourself. You know what's going on. Do it yourself. Add new features only. That's the only way they do it. Next slide. If you want to start over and do something good, next slide. Did we lose the next slide?
So it changed it. Now it says create trust, so people use your code.
Oh, okay. I missed mine froze on my side. Okay. Great. Thank you. Now it shows up on my side. Okay. So yes, again, library developers, you have to create trust so that people use your code. If you want people to use your code. If you don't want people to use your code, why are you running a library? Don't make it open source. Don't let other people use it. Okay. And the slide previous to this one was talking about major breaks. If you want to make a major break, it's a fresh start, no new users, you're writing a whole new library. Why are you even doing this? You can do this, but you better go support your old one as well, because people are using it to try and get people to upgrade to a new version, GTK 1 versus 2 versus 3. That's just a pain. It's hard. I wouldn't do that. And then next slide, never violate that trust on purpose. I've seen that happen a lot of times. And then slide stopped for me. What slide are we on now?
Yeah, it still says never violate that trust.
Okay. And this is the reason why I couldn't do it. It went too slow. So if you go to the next slide, it says application developers.
Now it does.
Okay, thank you. Application developers, next slide. It's the trick of application developers is you're the most easy and most visible to criticize. You are there. Next slide. It's like a traffic engineer. Everyone wants to know has an opinion where to put the road, where to put the path, what to do there. Application developers have a really tough time with that. Everybody likes doing that stuff. So if you go to the next slide, you need to be very, very careful about taking away things that actually work. And by things that actually work is if you have an application and a feature, people are using it, don't delete it, don't remove it. I mean, Emacs infamously keeps adding more and more stuff, then add more and more stuff, because you don't want to take the old stuff that wants to go. Next slide. I'm not seeing any slides, but I'll look for that. The April 6, 2011 is when, if you go to the next slide, GNOME 3 happened to the world. People call that the day your system broke. That system broke. GNOME 3 broke everybody's workflow. And by doing so, it made everybody mad, and it made people leave the project. It violated the trust that developers had with their users. That was a huge problem. People have grown to get used to it over time. But in a way, if you go to the next slide, that was the day that GNOME realized that they actually had users. that they weren't just developers. And a lot of open source projects have this problem. They just feel like they're creating it for themselves, which is great, and that's fine, but admit that. Admit that you're only doing this for yourself, not for a user. You have to be able to do that. If you are doing it for a user, you have to listen to them and then hope they use it. If you go to the next slide, it turned out that that was the day known developers broke users' trust. And a lot of people fled, a lot of people left. It made people really mad, even more so than normal. If you go to the next slide, there's a link to the review on lwn.net, and then read the comments and read the article. And it goes into that. It basically, you, without warning, broke everybody's workflow. And that's not okay. It really is not something, if people rely on you to do their work, again, you use these tools to do your job or do the task you want to do. Your task is not to just use the program. Your task is to do something else. You broke that. So if you go to the next slide, Mate and Cinnamon actually felt a real need. Those were forks of GNOME at the time. I see systems come with Cinnamon still installed. Cinnamon is still actively developed. It was a fork of the GNOME 2. Mate is the same idea, and in some distros, these still fill a real need. I mean, people use old TWM, WWM, so people use old window managers because that was their workflow. They're used to it and they like it, and then let them do their real job. Don't question that. Make a new one if you want, but don't forget that. So we go to the next slide. When you're an application developer, there's two ways you can change and to do this stuff, to get people to come along with you. Next slide. You can evolve really, really slowly and hope that nobody notices. And this actually works because you evolve slowly over time. It's like Linux kernel. You evolve into this crazy micro kernel architecture that handles asynchronous I/O at line speeds for gigabit or 100 gigabit networking in ways that the old model of the way the Linux kernel worked did not work at all. With new APIs. The old APIs didn't work that way. You can evolve slowly, and I will call out, if you go to the next slide, KDE is a great example of this. They've evolved slowly. They do have new visual refreshes, but they didn't break people's use. I've used this talk before, and then somebody said, oh, KDE X number of what broke my use case. I'm like, did they fix it? I'm like, yeah. Okay. Are you still using it? Yeah. I'm like, okay. They evolved slowly, kind of worked it, but KDE realizes they have users, and they want to use they respect their users that way, and that's a good thing to see. So that's one acceptable way to evolve. Another acceptable way to make people change, if you go to the next slide, is you have to provide a really, really, really good reason to make that leap. And you have to provide something that's just so much better and that solves the problem so well that you're going to have to change, and you want to change. So if you go to the next slide, the perfect example of this is everybody's lightning rod, Systemd. Systemd was a conglomeration of all the different people that worked at the low level of the Linux operating system, right above the kernel, the low level plumbing, and they put it all together and they figured out, here's the solutions for all this type of stuff. And they created this new solution and they got everybody out to do this stuff. It broke people's existing systems, or it broke their existing ways of using it. So much so, huge arguments, lots of people hated it, distros forked, some said they wouldn't do that. But if you look, over time, the majority of the systems out there are running Systemd because it solved a real problem and it was a compelling solution to the existing problem that people had. That's the way you do it. It's not especially nice, but it does work. So, next slide. Applications never break the user's trust or they'll leave. GNOME 3 found out that. They've clawed back. I think they now have more users because the number of people using computers and GNOME has grown, but they did not. That is a good thing. They broke the user's trust. Some people will never forgive them. So again, go to the next slide. This famous quote that's been said before, if you make your users mad, they won't be your users anymore. It's that simple. But when this comes to security and updates, you want people to take your updates. So again, if you go to the next slide, if you make your users mad, they will run known insecure software. I have seen this. I have seen this in Linux kernel versions where people are afraid to upgrade because they feel like there might be some breakage or somewhere, even though we insist there won't be. And if they test, there isn't, but they're afraid of that. And because they were burned or another vendor did that or something, they will run known insecure software just because they're afraid of a unknown. And that's really, really bad, horribly bad for security. You would much rather have unknown new issues than known vulnerabilities that people can take advantage of. It's that simple. The odds are that's just the way things work. And through our testing, we want to know if there are problems, we'll fix them. It's that simple. We can't fix old stuff. We've already fixed it. Take our fixes. We're giving it to you for free. And we didn't break your use case. That's our requirements. So final slide. Again, the most secure systems. Go to the next one. I can't see it, but I'll assume it's there. The next slide that says the most secure systems are trivial to upgrade and they don't make their users mad. It's that simple. That's the most secure system because you have to update your system. Systems that never updated are dead. Operating systems that do not update are dead because the world changes, the world evolves, or they're just not interacting with any external entities. If they don't interoperate with anything else, then sure, they can stay static. The world does not stay static. You have to update based on that. So you have to change your model. You have to be able to update, and they have to be able to upgrade. If you are creating a system that can't be upgraded, or it's difficult to upgrade, or it makes your users mad and take time to upgrade, they won't do it. They'll be insecure. And that's not good. That's my undocumented, because it's not talked about in lots and lots of literature about making secure systems. It's you have to be able to upgrade, and you can't make your users mad. It's that simple. It's the human element, and it's forgotten about that. So thank you very much. That was fast. I got plenty of time for questions. There's one more slide if you want pretty pictures of penguins, and I can answer some questions.
Okay, thank you.
Okay, I see a question on the chat. I can answer that if you want me to.
So, what? So there's a question from Matthias Payer. He's on YouTube. He says Linux follows extreme positions. The kernel user level interface, no API can change, but inside the kernel, APIs change all the time. So given the increasing size of the kernel, why not enforce some API constraints inside the kernel?
There's no need to. Linux kernel is unique in that it changed the model of having to make that hard boundary between drivers and the rest of the core kernel. It turns out all operating systems break that API, that break that line there. It just isn't there. If you look at Windows breaks it, BSDs break it, all the operating systems break it. Because you can't make a stable API at that level without a lot of overhead. Infamously, Microsoft, when they introduced USB 3, had to write a whole new API because they had to try and keep old APIs around. We rewrote the current API and away it went. Linux kernel is a monolithic kernel. You run everything in the same address space. It's smaller because of that. On average, Linux drivers, because we can change the API, are 1/3 the size of other operating system drivers. So we will take that size decrease. Size decrease means it's more secure, means it has less bugs, and it works better. So we keep our API active inside the kernel. There's no reason for you to ever need to keep your code outside the kernel. We will take anything in the kernel. I will take anything in the staging directory as long as it builds, and sometimes it even doesn't have to build. And we will have people fix it up for you. So away you go. Get the code in the kernel. The APIs evolve with you over time. You don't get, if an API evolves in the kernel, you don't have to change it. The person changing the API changes your code for you. They did your work for you. That's our model, and it's worked really, really well.
So maybe the question is going around the other way, and maybe he wonders why we don't cut out more things inside the kernel.
We do. So the kernel is very monolithic. What do we have? 30 million lines of code these days. But my laptop only runs 1.9 million lines of code. My phone runs 3 million lines of code because the SOCs are more complex. So we do cut out things, but things that are in the kernel that nobody uses are not dead weight because they're just not being used. And over time, we are removing things. I just saw a bunch of patches that went by today that removed a whole bunch of old media drivers for video cards that aren't around anymore, or cameras that are not around anymore. If you know of things that are not even around anymore, let us know, and we'll gladly delete them. Well, we love deleting code. But since everything's monolithic and everything's modules, drivers don't interact with other drivers. So if nobody's using that driver, it's fine because it's not causing any dead weight on you. You're not loaded into your system. It's not any harm.
Okay, thank you. So the next question. So the next person is here. So I'll read the questions, but if the person is here and if you would like to follow up, please, I think there's a way you can do that. So next person is Alfonso de Grigori. Greg, thanks for your talk and work at the Linux Foundation. In 1998, a colleague now working in offensive security published on BugTrack a proposal for a patch to A vulnerable network daemon. The very simple patch contained a backdoor, but nobody noticed. Would you comment on the hypocrite commits by University of Minnesota, please? For what reasons? Certainly understandable from both a human and professional point of view. For example, complexity, trust, workload. A malicious patch is mistaken for a benevolent contribution to the code base.
Sure. So for those of you who don't know, University of Minnesota published a paper, or tried to publish a paper at the beginning of this year about that they purposely submitted bad patches to the kernel process, and they wanted to see what would happen. The paper claimed that they were accepted. It turns out all the patches that they sent us were rejected except for one, which was actually correct. The authors tried to write a bad patch, but it was correct. So we accepted it. That being said, they were trying to, I mean, that's just mean to us. We don't look at individuals in a trust basis for trustworthy code. The only Linux kernel development is about trust. It's about trust that you're going to be there to fix the problems that you create. I want the infrastructure in place to fix and find all the bugs that I make. Because if you look, the number of bugs created by, the most bugs created by the smallest number of people are our core developers. So we are human, so we make mistakes. Infamously, there's a TTY bug that I created. I fixed it. 3 years later, somebody realized there's a hole and all Red Hat systems could be broken. We need to have infrastructure in place so that when I submit a patch that is broken, it is caught. And we have the infrastructure now with our testing, with our set analysis tools, with our review, this stuff can work. Of course, we're human, things slip through, but our trust model is we want to trust not necessarily that you got it right, but that you're going to be here to fix it when you get it wrong, because everybody gets it wrong. So I take patches from people I trust because they have a good track record of getting right, but because their track record is perfect for fixing it when they get it wrong. And that's the model. You have to gain that trust from other people when you come into our community. You can easily get patches into the external part, into drivers. University of Minnesota people were trying to fix error path cleanup code on obsolete drivers. We went back through and audited all the drivers, all the patches that they submitted over time. Their rejection rate was huge because it turned out they got the error path cleanup code wrong in a number of places. But as an example, we were arguing over the Sega Dreamcast CD-ROM player from 20 years ago on how to clean up an error path that, I mean, nobody ever hit this error path, obviously. And if they did, they would just leak a few bytes of memory and away it went. The system wasn't a big deal. It's easy to get changes and fixes into those type of things that are not critical. It's really hard to get to the core parts of the kernel. The networking developers, it's very hard to get core fixes in there. Scheduler, I mean, really trying to get scheduler fixes in there. It's very difficult to get scheduler fixes in because these are core parts of the kernel that everybody relies on. Those developers are normally naturally evasive when it takes changes from other people because they have to now support their work. Like we have a good example with networking. Somebody submitted a big feature. Once it finally got merged, the day after it got merged, the email address disappeared off the internet. It was gone. And it took the network developers 6 months to unwind the mess. So they do not want to do that again. So you have to earn the trust that you will be there to fix it when you get it wrong. And that's our trust model. Again, we all get it wrong. I get it wrong. Our testing and security model needs to be that we catch it when everybody gets it wrong because we're just human. And with our testing and infrastructure we have, we can always do better, but that's our goal. And that's what we need to do. And that's how we work.
Okay, thank you. Roland Yap says, so this is just a comment. LLVM is an example of a system which makes it hard to upgrade.
Compilers are tough, yeah. But your distro makes a new compiler. Yeah, anyway, I'm not going to go there.
So actually, I had a question about upgrading like the application level or the library level. So I've seen some other research where the person looked into whether, like, what systems kind of do well in the long term. Do they do well if they keep a stable API forever? Do they do well if they do whatever they want? Kind of your developers don't even know they have users, they just do their thing. Or do they do well if they do whatever they want, but they provide some kind of upgrade path? some kind of easy tools or something like that so you can upgrade your code. And one thing that he found was that projects that were taking a very rigid approach to we have to keep the APIs, we have to keep everything the same forever, maybe they were keeping their users happy. And I personally, as a user, would be very happy with that kind of project. I don't want anything to change ever. But they were not keeping their developer community happy because their developer community felt like they were in a straitjacket and they could never propose any kind of new design because it would go against some existing thing. So
that's very true. I mean, it's all domain specific though, right? I mean, if you look at an operating system, we can do this. The Java operating system is to abstract hardware away so you can run your applications, right? So we want to provide a stable API for other people to use stuff. It's hard to write easy to write an operating system kernel. It's really hard to write an operating system drivers. So people use Linux for that. You can evolve it over time and just keep adding new stuff. We change our internals all the time and we don't break APIs outside. But our APIs structures is very, very thin. It's very tiny. I mean, if you look at windowing managers and libraries for that stuff, their APIs are huge, and evolving that over time is tough. But again, maybe the easiest thing to do is then you just fork the project and you go off on a different way and see what happens. I mean, it's evolution, right? See how what if those developers are willing to grab the other users and have them do that work. But it's up to them. It's running a project. That's a tough call. We've made our decision on what we think it works well, and so far that's been the right solution, we think, for the kernel.
Mm-hmm. Yeah, I mean, maybe you could also though argue that happy developers make more secure systems.
Yeah,
and
maybe.
Fed up developers
don't. That's very true, but then yeah, it's tough. Yeah, we're keeping our developers happy because we're changing our internal APIs, and what we have to keep stable is almost trivial to us, right? Yeah. So it's easy for us to do. Yeah.
Okay. Another question is from Nikhil. Many new kernel bugs are reported by Sysbot every week. Some take a while to fix, presumably because they're too many. Does it help Sysbot say if says would it? Yeah. Sorry, this is not from Nikhil. This is from Jian on YouTube. Does it help if Sysbot says which bug is a security critical so that they can be prioritized?
It's really hard to determine automatically whether something is security critical or not. Sysbot hits things from user space, right? That's its goal. It's fuzzing and it does level. Whether the Sysbot program is running as root, whether it's running under specific kernel configurations that are odd, whether it's emulating fake USB devices, it reports all that stuff. So it's up to us as humans to interpret that as stuff. Sysbot's problem is that it finds more bugs than we can fix because we fix them all at one level and it's like, great, and now it can fuzz one more level lower and go. That being said, there's a lot of Sysbot bugs we are learning to just ignore. You can do fault injection with Sysbot and you can say, I'm gonna break this, this memory allocation is gonna stop. We're gonna fail this memory allocation. When in reality, I know that memory allocation can never fail because it's on the boot path and the machine is starting up. So I'm just not gonna worry about fixing that stuff. I run to a Conda Foundation intern project. We have 10 interns every 3 months that work on just fixing these bugs. This takes more work. Again, the Sysbot people are finding more bugs than we can fix. Send us more resources. That's why I talk to Google all the time. They're like, why aren't these being fixed? I'm like, you have the resources to fix them if you care about it. So automatic prioritization of bugs is very, very difficult. We don't know how to do it. And infamously, I've fixed bugs that I thought was just a normal bug. It turns out they're a security bug. If I can't be trusted to get this stuff right, who can?
Okay. So the next question, this is from Derek McKee on YouTube. Adding on to the fuzzing question, is it worthwhile to ease integration of fuzzers deeper into the kernel, or will that dramatically increase the code size attack surface?
We have eased fuzzers into the kernel. We have, like I said, USB. We have a fake USB host driver that can emulate a USB device on a loopback internally and do some crazy, crazy things with USB devices that we can't do in real life. And it's found a lot of layers because that's a new model. So there's a new threat model. Now, all of a sudden, we cannot trust USB devices to be what they say they are. So operating systems traditionally could. Now we can't. The fuzzing is integrated into the kernel, and that layer is there so that it can take advantage of it and fuzz deeper. They're doing the same thing for Bluetooth now, for networking devices. They're integrated into the kernel. And the Sysbot developers are great. They're doing the work. They've added the hooks in the kernel. We've got KSAN, other types of stuff for finding UVSAN, for finding memory overflows or memory bugs are used after free. We find all these stuff that's integrated into the kernel. So yes, we welcome it, and it's there today. It's actively happening.
Okay. Next question is, this is from Matthias Payer again, also from YouTube. What is the cost-benefit trade-off for new mitigations in the kernel? CFI is useful in user space, but the kernel contains very juicy data-only targets. So write-once protection may be more beneficial.
So we now have CFI in the kernel. So that just got merged a few weeks ago. It's been shipping in Android devices for at least a year, though. So it's been out there for a while in the real world. That is a real thing. What is the cost-benefit trade-off? A number of years ago, we used to say if any security or any mitigation cost us time or energy, we wouldn't accept it. We changed our mind about 8 years ago, I think it was. A really good presentation by Konstantin talked about kernel needs airbags. Case Cook, we're into kernel hardening project. We will accept trade-offs in increased developer time, like we now hide pointers. They can't see what they are in user space kernel pointers. We don't let that escape to user space. And we will also accept trade-offs for certain runtime slowdowns, but we make it an option. You don't have to select that. We have a whole number of kernel configuration options that are like initialize all memory to 0 or free memory when it's overwrite memory when it's free. That you can enable for your kernel configuration if you want to. I work a lot with Android kernel developers. They have a list of kernel mitigation configuration items that they recommend and that they require. And yes, they will slow down your device, but they feel it's worth the trade-off because hardware keeps getting faster. So yes, it's a cost-benefit trade-off. We provide the ability for you to turn that off if you want and turn on if you want to as well. Again, CFI is there. One disadvantage of CFI from a developer's point of view, it takes my builds from less than 5 minutes to 15, 20 minutes based on the tools that we currently have. So that's a slowdown. Is it worth it or not? You turn on your development, on your build that goes off to other people, you turn it off on your development builds and you work with it that way.
Okay. This is, I think, from Nikhil himself. I've read some online discussion about the possibility of using Rust in the Linux kernel. What would you be able to comment about the likelihood of that, the cost benefit, and any progress in that direction?
Yes, I have spent some time working with these developers. Linus and I heard from them many years ago, and we said, sure, let's see if it'll work. They posted it. I've actually written it and worked on it and got it to work on my machine and wrote a Hello World module. The whole university fiasco took up my time. I wanted to learn Rust better, but it's active. It's active, and people are actively working on it. Whether it is viable or not remains to be seen. There's a whole bunch of really tricky issues that they're going to have to negotiate. And the biggest one is, and they haven't come up how to do this, is the kernel has objects, and these objects have lifetime rules. They're C objects. We do memory management. We do object-oriented programming in C with multiple inheritance and other fun type of stuff, reference counted. That's going to have to cross the C to Rust barrier somehow and preserve the inheritance and preserve the memory safetyness across that barrier somehow. That's going to be tricky to see. Developers know about it. Let's see what happens. They're talking about just using it for some leaf nodes on the kernel as far as modules go. The problem with leaf nodes, drivers are actually one of the more complex things. They use more parts of the kernel than some of the core parts of the kernel do. So it's going to be interesting to see what they do. There's some example modules out there. I wrote a dev0 example in Rust. It's pretty simple to do. They have a character device. They're trying to work on the binder driver to see if that'll work. I pointed some interns at it to see if they can write a virtual file system that's in-memory file system, and they're writing the APIs. So it's fun. Let's see what happens. It'll be interesting to see. They have a whole bunch of things to go. They have a lot of work to go. But that being said, I'm excited to see what they do come up with. And hey, it's research. It's evolution. Let's see if it evolves into something that we can use. We're not saying no.
Okay, so I have a question. So a lot of problems, security problems or just general crashes, unreliability or whatever, are related to concurrency problems. And I mean, in the kernel, there's a lot of locks and there's a lot of data structures, and it's not really apparent all the time how all these things fit together. So, I mean, I've been at a kernel conference with experts in a particular subsystem where the speaker was saying, okay, there are 3 locks here. I understand the first 2. I don't know why the third one is here. Is there anyone in the room who remembers why the third one is here? So should we have some kind of annotations or something like that if it could be produced automatically, perhaps?
Yes. We have a way of trying to annotate some things. We have lockback, which shows the dependency ordering of things, and when we get it wrong, which will run at runtime, we used to have a way that functions could be, say, I need this lock or I'm going to require this lock. It never really caught on, but the infrastructure is there to do it if you want to do it. That being said, this is a system that has evolved over time. I had a fun time talking to the Fuchsia developers about a year ago, like, oh, look, we got to do all this cool stuff and we know it's right, it's perfect. I'm like, that's great. Talk to me in 20 years when your system has evolved over time. When you lose developers, I mean, we have 4,000 developers a year and you kind of forget what was going on there. That being said, the developers that work on the kernel know this stuff. We know this stuff better than anybody else. So yes, and we forget things. We would love to have ways to better annotate stuff. The goal is to write code with don't leave locks, or you have reference counts or things like that that work automatically. RCU has helped out a lot. The big problem with RCU is there used to only be 1 person that understood it. Now I think there's like 2.5 people that understand it. So it's getting better that way. You don't want to have a bus factor for RCU. But yes, we would love that. I mean, there is increased complexity when you're dealing with a lot of these crazy things. Hopefully you can look through the archives. You can see our discussions, thanks to everything being an email. We had a lot of problem going on the pre-Git days before 2005 to try and remember what happened then. We still have some code that's around that was written back then too. So trying to remember what was understanding and what was happening there is tough. But yeah, I'd love to see more annotation, more way to document that if we have it.
Okay. Let's see. This is from Warren Wang. When I worked on hunting kernel bugs, I found the fixes for bugs in the same source files were not accepted because these files are stale and not used. So why not just remove those files from the kernel?
We should. If you submit things and they're not being used, we should. That being said, getting your patches accepted is hard to find. We have a problem of we have too many developers, not enough maintainers and reviewers. So us maintainers rely on other people to help us with the review. So if you want to submit code and get it accepted, start reviewing other people's code. If I see somebody else reviewed something, I'm like, okay, that's good. At least it's past 1 set of eyes, and I can go and look at it. A lot of the corners of the kernel that aren't being maintained get swept up by like Andrew Morden or the trivial tree, or I've been sweeping up a lot of driver stuff. Just email it to other people. We have tools that'll say, for this file or this patch, who do I email it to? Never just send it out to a mailing list and not copy a developer on it. Otherwise, it will get lost. Or just resend it. I mean, we are all human. We're lossy. We drop things out after time. So if you don't get a response in 2 weeks, send it again. If you found problems that were fixed and nobody picked them up, send them again. We will take them. It's just human nature and stuff like that. We need more people to maintain code. If it isn't being actually maintained, I had one of my interns fix some sysbot bugs in one part of the kernel. It turned out nobody else was doing it, and he became the maintainer because nobody else wanted to maintain it, and nobody else was doing it. And that was surprising to him, but that's the way it works. Because if you want to maintain it, wonderful, great. Or if it's not being used, we'll delete it. No problem.
Okay. So did I miss any questions?
Don't think so.
I think you got them all.
Okay. So
Great.
thanks, everyone. Just a small announcement. In 2 more weeks, there will be a talk from Deepak Garg of the Max Planck Institute at the same time on June 16th. So thank you.
Great. Thank you.